Good afternoon to all of you. And you're all in Jawaharlal Nehru Planetarium, Bengaluru. Jain Planetarium, which is administered by Bengaluru Association for Science Education, is a major center for the dissemination of science, all of you know very well. And two of the main streams of activities of this great institution include non-formal science education as well as science popularization. I'll come to the second one first. Pertaining to science popularization, there are myriad activities, many of them, including shows, theme park, popular lectures, Ask an Astronomer, and so on. Apart from that, special events like Copy with Curiosity, and of course, Dasara Lectures. The other stream, which is non-formal education, and it is equally important and includes REAP, Research Education Advancement Program. This is mainly for undergrads, okay, and degree students basically in physics and biology. And of course, we have weekend lectures for high school and pre-university students. These are all part of non-formal education, which is as important as science popularization. Today, of course, we have assembled here for the inaugural Dasara Lecture of 2023 today. And for this, Professor Shiv Sethi of Raman Research Institute has kindly consented, and he has come here to give the talk. And of course, the title of the talk is very interesting and exciting indeed, The Distance Ladder in the Universe. All of you know how important it is to quantify the universe as such. It is not that universe is this big, that big, and all those. As a scientist, you have to explain that. And I don't want to take much time at all. And I once again thank and welcome Professor Shiv Sethi for this kind gesture of coming here and delivering the inaugural talk of the inaugural lecture of the Dasara Lecture series of this year. Thank you, sir. Thank you very much. Now I invite Sharanya, please.
Thank you, sir. A short introduction about the speaker. Professor Shiv Sethi is a cosmologist. He did his PhD from Delhi University. After postdoctoral stints at IUCAA Pune and IAP Paris, he joined HRI Allahabad as a faculty member. He then moved to RRI Raman Research Institute in 2002, and he's currently a professor there. He has also held visiting faculty positions at Carnegie Mellon University, USA, and IIT Madras. I thank him very much on the behalf of Planetarium for accepting to give this talk on this occasion. And I request our director to hand over a memento from our side. The stage is all yours, sir. Thank you.
We'll change the slide and sure.
That's the list.
Correct. That I can see. Yeah. can start now. So you can hear me at the back, right? Okay. So it is my pleasure to be here, and again, I thank you for a warm welcome here, and it is really my pleasure and privilege to be here, and I have not been here in many years, so I look forward to coming here more often than I have in the past. And in this talk, I'm going to talk about distance ladder in the universe. So let me just flash my first slide. So people, when you ask the question, and I'm going to address school students here, and I believe that all of you are school students, and no concept I'm going to use during this lecture will involve anything more than roughly an understanding at maybe 12th level. I mean, I'm going to introduce concepts which are higher than that, but I'll try to explain them as much as possible. So how do you measure distance to a faraway object? If I ask you the following question, you would say, well, I will walk up to that, or I will drive something that, and I'll come back and I will look at how long it took. But you know, you can't drive to faraway objects. You can't drive to even moon moon and sun you can probably go close. Moon, of course, you can go to. But how about going to a star? How do I know a distance to a star? How do we even measure it? Can you hear me? It's uneven? It's fine, right? So how do you do that? Now that is not an entirely straightforward question, and this has required 2 centuries of effort to reach where we are today. Typically, there are 4 ways of measuring distances to any object. First is called the parallax, and I'm going to explain to you what parallax means. Again, it's a geometric concept understandable to anybody with a school level education. Second, something that is used a lot in astronomy, and we use it all the time, is something called luminosity flux relation. Basically, what we have, I'm fine, right? I can be heard. Sometimes it seems to me I'm not heard. What we have is, we have some objects very, very far away, and it is emitting energy in our direction. Photons, you call them electromagnetic waves, you call them photons, at a certain rate. Something called L, that is luminosity, and it has units of energy per unit time, right? Like you say, this bulb here is 40 watts. Watt is the unit of energy per unit time, right? That light, basically, let's imagine an isotropic source. If I had a board here, I would draw it for you. But let's imagine an isotropic source, and that energy spreads out in a sphere of increasing radius as the light moves further and further away from the source. You can imagine a sphere in your mind. Now, far away on a sphere where we are, we have put a telescope which intercepts a part of this sphere, right? And that's what we measure. And what we measure is what is called flux, that is the left-hand side, right? What we measure is flux, what is intrinsic is luminosity, and they are related by a distance, 4 pi r square, right? That is the distance to the source, right? So you would immediately say, okay, how do I measure distance using this? Because I measure flux, but I don't know luminosity. Do I? Of course I don't. I try to infer luminosity by measuring the flux. So there ought to be something else. There is one more step here before I can utilize this method. And I will tell you what that additional step is. This is one way to measure distance. The other way to measure a distance is what is called angular size diameter relation. You have an object far away, and it is subtending an angle at you, right? You understand subtending an angle at you. You have an extended object, and it subtends an angle at you. Moon subtends an angle of half a degree on us. So does sun, by the way, right? That's why you have solar eclipses, right? They have equal angles on the sky. So half a degree is the angle subtended by moon, by sun, and all the other objects, of course, the angle they subtends on us is far smaller than the angular resolution of our eye. So they look like point objects to us. They don't look like extended objects. Here again, suppose I can measure theta, which is the angle subtended by an object, and if I know the intrinsic size of the object, then I can measure r, the distance to the object, right? But then again you would object and says, how do I know the intrinsic size of the object? Because that's what we are trying to actually measure by measuring theta in the first place. So again, another step is needed before I am able to say something about d, right? How do I know the intrinsic size of, for instance, sun? That is the second method. The third method here. The fourth method is the relation between something is moving across the sky, like this. So it moves at a rate theta dot, which is the rate at which the angle across the sky is changed. And the relation between that, v is the absolute velocity on the sky, but I don't know v. I don't know what the velocity is. I can only measure the change in the angle at us. And the relation between them again is mediated by a distance, which is r. Right? Yet again, you would say, how do you know how fast that object is moving? You can only measure its angular position. Yet again, there is an intermediate step that is needed before I can measure the distance using this trick. I'm going to talk about these four techniques in various different contexts throughout the talk. Let me start with parallax. So first, I will show you the geometry of parallax, and then we will go into how it works. So idea of parallax is strikingly simple. You have Earth, you have Earth which is going around the sun, right? And this mean distance between Earth and the sun is 1 AU. That's called 1 AU. Did you know about this? One astronomical unit is defined like this. The mean distance between Earth and sun. It's actually, the orbit is almost circular, right? So, well, it goes around the sun. Every 1 year it comes back to its original position. But every 6 months, it's on the opposite side of the sun, right? It starts from here, 6 months later it reaches somewhere. Now I look at an object in the sky, a star, and I try to find its angular position vis-a-vis stars which are even further away, right? So this star, this yellow thing is the thing closest to me, and there are things even further away. How will it look in the sky? When the Earth is here, it will look here. It will seem to be here. When the Earth has moved to the further point on exactly the opposite side, this object has moved its position with respect to the background stars. Let's say the background stars are at infinity for simplicity, right? They are very far away, right? Now the shift in this angular position of the star with respect to other stars is called the parallax of the star, right? And this half angle is called the parallax, right? And that is how we actually define, and now I'll go back to the previous, the next one. This is how we define what's called a parsec. All the units of distances in the universe are derived using a parallax. A parsec is 3 into 10 power 18 centimeters. It's roughly 3 light years. A parsec is what? Parsec is the distance to the object which subtends an angle of an arc second through parallax on us. 1 AU is this number, this is 1 parsec, and this angle is 1 arc second. So if it is 1 arc second, this is called parsec. So parsec defines the unit of distance in the universe, and it is defined using what is called the parallax. So this is what it is. Distance to a star is roughly 1 by the parallax to that star in terms of parsecs. Very good. When was the first parallax measurement done? First parallax measurement was done actually in 1838, this is not that long ago. So before this, we really had no idea how far stars were. First time it was measured, the first parallax measurement was around 0.29 arc seconds, seconds of an arc, which was made only in 1838. Since then, we are going to smaller and smaller parallaxes. That's how progress happens. That's what technology is, right? So that was the first measurement. The largest that we know is for the nearest star, and the nearest star to Earth is Alpha Centauri, and it has a parallax of around 1/4 of an arc second, 3/4 of an arc second. This is the nearest star, which is at a distance of 1.3 parsec. If this is history, this is the present. So all throughout 20th century, people kept improving. They tried to measure distance to further and further object. From Earth, you can get a parallax of around 0.05 seconds of an arc, which gives you a distance of only 20 parsec, just 20 parsec. To give you a sense, our galaxy is around 20 kiloparsec, 1000 times larger. So from Earth, we can only measure a parallax of around 20 parsec. So people then thought they should go out into the space. And this thing happened in 1990s, 1838 to 1990s, when the first such satellite called Hipparchus was launched. And Hipparchus actually measured parallaxes of roughly 0.005. It improved it by a factor of 10 roughly. So it measured distances quite precisely up to 200 parsec, 10 times further, right? of 120,000 stars. From Earth base, we can only get around 1,000 stars. Only 1,000 stars are close enough that we can measure their parallaxes. With Hipparchus, we went to 120,000 stars. There is currently an ongoing mission called Gaia. All of this that I am writing here, you can note it down, or I can just give my slides to you. Because when I speak here, I have it in my mind that all of you guys are very good in checking. You can always go and check. All you have to do is to say Gaia parallax and you'll get all the information about it. So I will keep the information to a minimum, realizing that you people can actually check it on your own, right? This information is a stepping stone for you, that one I am giving. If you are interested, you will go and check. So please go and check Gaia. And this is still an ongoing mission. Already since 2014, it has measured distances up to 10 kiloparsec. Now it has gone even further, right? Of almost 100 million stars. So Gaia has taken us to the edge of the galaxy. I said the galaxy was 220 kiloparsec. Almost to the edge of our galaxy, we can now measure distances directly using parallax of roughly 100 million stars. You may ask, why 100 million stars and why not a billion stars? The answer to that question is, not only that star has to be near enough, it also has to be bright enough as far as the satellite is concerned, right? So this has a brightness limit, and I'm not going to give you those limits because you guys are smart enough, you go and check for yourself, right? What the specification of the telescope and what it has actually achieved. But based on what I have told you just now, you can make sense out of the mission aims of Gaia. I will move on and I'll talk about a distance, another distance measure of historic interest actually, of great historic interest, called the moving cluster method. So again, I'll be brief here. What we have here is a different setting. We have, I'll go to the next one. This is slightly poor condition here. So just bear with me. You have an open cluster. You have a cluster of star. This is called an open cluster. And that is moving away from you, right? By its motion away from you, you are able to measure its distance. I mean, you can do it with a car also. Think about it, the same method you would use actually. So what you really do is, this point, this is moving away from you, and it is converging towards some point. You will never reach the point of convergence. That will take millions of years, but you can reconstruct it. So what you do basically is, by changing, so what you are doing here again, you are using the change of an angle here along your line of sight, right? So this is the change of angle in a given time dt. So you take the data now. Some of these stars have been observed for 60 years. Star clusters have been used for 60 years. So in 60 years, d theta by dt has improved. You have actually seen the change. The angle that stars have subtended on you has decreased because it has receded from you. You can actually measure this. And that you can construct. Basically, you can measure d dot, the change in the distance away from you through Doppler shifts. And based on that, you can actually construct a distance to the object. So yet again, I will be brief here, and I will expect you, after having introduced you to this concept, to check on your own. Okay. Similarly, you can actually compute what's called the convergent point, and I will not say much about it. I've just left it here. You can make use of my slides later on and check for yourself. I mean, I myself do it, like I go to the internet and check this convergent point moving cluster method, and it will give you all the information that you require. And like I said, you require information. You require understanding of just very simple geometry to understand any of that. So all the school students who are sitting here will understand what is being said here. This method has been successfully applied to just 4 clusters. In an effort lasting 200 years, only 4 clusters, this kind of a distance measure is possible. So it's of historic interest, but I wanted to give you a sense of this to just underline how difficult it is to do this. It's not easy to do it. But because it gives you an alternative way of measuring distance, it is of paramount interest. Because I can use one method and I can use another method to calibrate that method. And that is something we always need to do. So only 4 clusters, and they are all close by actually, you see. The furthest off is this 170 parsec. So this is not as effective as parallax is, right? But of great historic importance, the way it has been applied. Now I'll move to this very interesting object, which is really the only object we have so far, to which the distance has been measured completely, directly, geometrically. And this is called a galaxy, it's called NGC 4258. This is a galaxy, and I'll show you the distance. This is 7-8 megaparsec away. So now, remember parallax was 10 kiloparsec, moving cluster was only 100 parsec. This has gone to megaparsec. This has a very interesting geometry which allows us to compute these distances. There is a black hole at the center and gas is going around it, and then there are further off from the black hole there are what are called water masers. And through radio astronomy interferometry, you can actually get angular resolution of all of these things very, very precisely. This geometry allows you to do the following. It allows you to construct the black hole mass in the first place at the center. Black hole is somewhere here at the center. This is, and in addition, it allows you to compute the acceleration of the particle. In real terms, an angular acceleration I can measure. So a relation between the two gives me a distance, and that's what I have written in this slide. So there are some water masers. Geometry is very simple. Don't worry about what water masers are. These are something which are very, very bright. That's all that it really means. So you can actually compute velocity as a function of distance for a Keplerian disk. And such a geometry actually allows us to compute centripetal acceleration of the water spots. The physical acceleration can be measured. It's around 9.5 kilometers per second per year. The angular acceleration can actually be measured by direct observation. And relation between the two gives you the distance to the object. So this is actually really interesting. You can compute the distance to the object in a very direct way using this technique. This distance is around 7 megaparsec. So this is the furthest we have actually ever gone using a method which is not parallax, which is not an absolute measure of anything. This object is unique in itself, that this is the only one of its kind. And this work started in 1990s, still ongoing of course, because recently somebody improved the measures, like only in 2020 there was a paper. But first time it was reported in early 2000s too, right? Only object to which distance is actually really extragalactic, 7 megaparsec, and it has been computed using purely geometric techniques. Now I'll come I have not missed anything. Sorry. Have I missed a slide here? Yeah, this slide I wanted to come back to now to give you a sense of where we are. So what we do while building a distance ladder, and first I will describe what a distance ladder is here. So what I discussed just now are these three methods with you: parallax, moving cluster method, and water maser, right? You see this 0.05 megaparsec, this was only in 2019. So the work on this particular object is still going on. So first you measure absolute distance to an object. And there are a handful of methods, there are a few more, but not that many. The best method for that is indeed parallax. Then you rely upon what's called relative distance measures, and I talked about 3 relative distance measures with you. So what it requires is you measure the luminosity of an object. You can't measure the luminosity, you measure the flux, but you gauge that I can actually get luminosity from flux through what are called standard candles. Standard candles are objects which have all the same luminosity. They are called standard candles because their luminosities are all the same. And I will show you what standard candles are. One class of standard candles that have been used are called Cepheid variables. So here observable flux can be turned into luminosity with absolute measure of distance. So point is this: let's say I have measured with parallax distance to an object. I measure flux from that object, but I can construct luminosity for that particular source because I already know the distance, right? Then I go further off and I measure flux from the same set of objects, but of these set of objects I do not have independent measure of distance, but I can calibrate using the one for which parallax measure was given to me. So this is called calibration, the process of calibration. Make one measurement and use it to do another measurement. So standard candles are Cepheid variable, the two most famous ones, and I am going to discuss both of them in some detail. And supernova 1A. And supernova 1A, this measurement actually won the Nobel Prize in physics in 2011. This particular distance measure, the supernova 1A. What typically happens is that you are never satisfied with one distance measure. You always are trying to get as many as possible. I've just listed a few. So Cepheid is calibrated with supernova 1a with what's called Telly-Fisher relation, what is called surface brightness fluctuation, tip of red giants, and it's all done for one cluster. There is a cluster called Virgo cluster for which all of this becomes possible. So you are able to cross calibrate all of these different techniques. So that lends credence to our distance measure. If so many different techniques are giving similar answers, you must be on the right track. It couldn't really be off too much. If there are standard candles, there are something called standard rulers in the universe. Standard rulers are, again, the ones for which the relation is between the angle subtended on you, right? I told you, the angle subtended by an extended object. Standard ruler is one for which the size of the object is the same, or roughly the same. Here, there is something called Sunyaev-Zeldovich effect from clusters of galaxies, and I will not talk about it. I have listed all of these things, you can check it, but this thing you will not understand, not at school level. This is a concept which requires more than school level to understand Sunyaev-Zeldovich effect. So you can read about it, but you will not understand it too much. You will understand it later in your life. And there is something even more complicated called barrier acoustic oscillation, which comes in cosmological setting, which also you will not understand, but like you can read about it if you feel like. I will not say anything more. Then suddenly, in the last 10 years or so, we have what are called standard sirens. You may have heard, all of you have heard about gravitational waves coming from distant sources. There are black hole binaries, there are black hole neutron star binaries, and there are neutron star binaries, right? So far, we have quite a few black hole binaries, just one neutron star binary, right? Which I'll come to a little later. They are standard sirens. So that object is emitting gravitational waves, but you actually can measure the distance to it by detection of the gravitational wave at your location, because the waveform of the gravitational waves gives away how far that object is. So they are called standard sirens. But only one case we have succeeded in doing it, which I'll return to a little later. So this is a technique which all of you will see grow to be an important technique in decades to come. So far only one, but in decades to come there will be many such cases of standard sirens. So this is the technique we use. I've just discussed this. Now I'm going to discuss this set of techniques. I'm not going to discuss standard ruler. I'm not going to discuss standard sirens. Most of the rest of my talk would be about standard candles, because standard candles are more important for an astronomical setting. So I'll go back now and go back to what are called Cepheid variables. So how do you construct a standard candle? What does it mean for an object to have the same luminosity, right? Well, an object doesn't have same luminosity, but it can have a correlation of a kind which we might use. So here what I have shown you is what is called an HR diagram of stars. So if you take stars in our galaxy and you plot them on y-axis, you have their absolute magnitude, which is a measure of luminosity. So on y-axis you have luminosity, on the x-axis you have their temperature. This is called spectral class here. Most of the stars, 90% of the stars fall on what are called the main sequence. Sun is a main sequence star. But then there are all kinds of interesting objects, white dwarfs, sub-dwarfs. The one we are interested in is what are called classical Cepheids, which lie in what is called the instability strip. They are unstable stars. They oscillate. They are not stable like Sun. They oscillate. So their luminosity change quite a lot actually, right, over a period of time. So these are the stars we are interested in. And one properties of this star, which was found by Leavitt in Hewitt in 1912, so this was discovered in 1912, this property I am talking about, is the fact that if you try to measure their magnitude, which is a measure of flux, and plot them against their period. So different Cepheids, they oscillate at different periods, some with 10 days, some with 100 days, some with 5 days. What people found was that there is a correlation, there is a clear correlation between the flux. If the flux is more from the object, the period is also more. That is what this shows. The period, if the flux is here, the period is here. So period and flux, they correlate with each other. Brighter object has longer period. Once you know this, so what do you do? Okay, this object has a period of 10 days. So if such an object I have seen where parallax can be measured, then, and if I find this object in a further away object, I know what its luminosity would be because I've already calibrated, luminosity. So now I can use this as a relative distance measure. And that's what is done. So these are stars with roughly 3 solar masses in instability strip. They oscillate with well-defined periods, and that's an important thing. And their luminosities correlate extremely well with the oscillation period, with a few days to a month. So first they were discovered in LMC. LMC is Large Magellanic Cloud, which is basically a satellite of Milky Way. It's around 50 kiloparsec away from us. For absolute magnitude from visible to near infrared, they can be actually determined to within 10%. Now people are claiming they can determine it to even better than that. 10% is a typical number. This was first used. So historically it is of great importance for the following reason. In 1920 there was a great debate, and I was just discussing with some people. The great debate was between Shapley and Curtis. There were two people who were asking the question, is there an extra galactic universe, or there is only our galaxy around us? The extra galaxies outside like Andromeda, they were called nebula. Nebula means something which is not well defined. So people believed that nebulas were actually inside our galaxy. But then somebody discovered Cepheid variables and started measuring distances to these and found that they are actually outside of our galaxy. They are not a part of our galaxy. They in fact lie well outside our galaxy. So this has importance in the sense that it allowed us for the first time to establish the extragalactic scale in 1920s. And as it turns out, they are still used the most to build the distance ladder as relative distance ladders. To jump from one point to another, you still use them. But is Cepheid enough? That's the next question. They are bright enough to go to a distance of 20 megaparsec. Right? So you see, again, let's look at the distance ladder. Parallax takes you to around 10 kiloparsec. This takes you to around 20 megaparsec using Hubble Space Telescope. But this is very important. You have jumped using this ladder. So there is a ladder you have used. One part of the ladder takes you up to a certain point. This ladder takes you well beyond that. HST discovered around 20 Cepheids in Virgo cluster, and this gives the distance to that cluster of 17 megaparsec. This is still being done. This is still being calibrated, and these distances are continuously being improved. But is 20 megaparsec enough in distance ladder? How do I go further? So this is where we stop, is it? 20 megaparsec. Is there another measure that allows us to go even further off than 20 megaparsec? Yes, there is. And that is what is supernova 1A. And that is why this one won a Nobel Prize actually, and this is from the Nobel Prize citation. I'm just quoting what was quoted there about supernova 1A. These are objects which occur in a binary system. In a binary system, there are two binary stars, and one of them blows up after it accretes matter from the other. And after blowing up, it actually has so much of energy, it outshines the entire galaxy. You see, if I'm going to go further off, I need to go with very bright objects. You see, the further the object it is, the fainter it would seem to us. So with Cepheids, I can go to 20 megaparsec. But Cepheids are too faint after that. They are after all stars. But this is not a normal star. This is a star which has burst into a supernova. And a supernova basically outshines the entire galaxy once it bursts. So I can go much further off with this. I will show you some properties of this. So this is yet again to show, here the point of next 3 slides is to show you how you actually test these properties of whether it is a good standard candle or not. Why should a supernova be a good standard candle, right? What has been done here is there are 22 supernova 1A in B band. B band is just an optical band. And they have been plotted. So supernova, what happens in a supernova is that when it bursts, it initially gets brighter, and after around 10 days or so, it begins to get fainter, and then it goes into this line, which is a flatter line, and physics of this is approximately understood. It's not fully understood even today. This is what this pattern supernova follows. When it bursts, it goes bright, Then after certain days, it goes faint and then flattens a bit on this strip. What has been shown here is 22 supernovas have been plotted on this light curve, where you see the change of flux for approximately 200 days. This is in terms of days. So you have plotted the rise. The rise is not easy to capture in most cases. You can capture the rise in some cases, but the fall is much easier to capture. The point of this slide is to underline the fact that there is a homogeneity in the properties of all supernova. All supernovas seem to behave similarly. If 22 are plotted here, they all seem to behave similarly, don't they? So there is a homogeneity in their properties of how their flux changes. That is very good. To build a standard candle, I need information like this, right? If all of them behave differently, I would say, what standard candle are you talking about? They all behave differently, right? There is no single property of theirs that I can use. Few supernova which have been plotted here, 3 of them. And the point is their spectra are also similar. 1 week after the supernova bursts, somebody has plotted their spectra, and most of the lines are similar, they are not the same. That's where a lot of work goes in actually, to check. So it is homogeneous as far as the light curve is concerned. Its spectral properties are also relatively homogeneous. That is the point of this slide. So I will show you this also before I will summarize this. Something very interesting happens in time scales in the universe, and that is what the point of this slide is. So something that locally happens, you will learn, you are right now in schools, you will learn something called special relativity when you grow older, right? In special relativity, there is an important concept called time dilation. Time from moving objects moves slower. You have heard that, right? Well, indeed it does. But in the universe, the further the object is, the slower time in it seems to move too. So this is not just a property of Doppler shift, it's also a property of the universe, expanding universe. So if something happens in 15 days for a local supernova, if I go to redshift of 1, that time scale becomes increased by a factor of 2. So what was 15 days here is 30 days there. So you can actually do that. What has been plotted here is, there are many of these supernova which has been used, plotted here from different redshift. They don't rise and fall at the same time because of the fact that 15 days if it took for it to rise and fall up to a certain point, now that will get stretched if the supernova is further off. But once you correct for it, but you know how far that object is, so you can correct for it. You have a theory to correct for it. Once you correct for it, they all lie on the same line. So it actually further underlines the fact that we can actually, so this is actually a proof in some way of the cosmological model of the universe. That yes, yet indeed, the time scales do stretch in a way and we can correct for it. So here what I have done is I have summarized some of what I have been trying to say about supernova 1A. First of all, it has an absolute magnitude. This number may not actually tell you much, but it is an incredibly bright thing. It outshines the entire galaxy. I said it once before, it does outshine the entire galaxy. What is also found is that the error in the absolute magnitude, remember we want to build a standard candle. I want an object which has the same luminosity. Its luminosity is not the same, it does have an error. And the error is large enough, but we can actually reduce it by using the fact that this luminosity also correlates with the flux in 15 days period. This is a very complicated thing, and we still do not fully understand it, but it decreases the error by a factor of at least 3. This was understood by people by 1990s, and this search for supernova at high redshift has been going on since 1990s. The first papers that were written were with 30 objects. Now we have close to 1,000. So current data, if you look at it, there are close to 1,000 objects. So this is again an outgoing thing. Sorry? The minus 90. This should be minus 90. Yeah. She has correctly pointed out absolute magnitudes are minus, right? This is a measure of luminosity, right? But in optical astronomy, they are defined as logs of luminosity. So minus is more. The minus number is more than the plus number. So you can check it for yourself. This is not my fault. These are the units which actually are used in astronomy, in optical astronomy. So this search has been going on since 1990s, and there are two projects, and they both won the Nobel Prize for this work in 2011, right? Where they actually could find supernova and took the distance ladder to a few thousand megaparsec. So from few tens of kiloparsec to 7 megaparsec for one object, to 20 megaparsec using CFIDs, to 1000 megaparsec using supernova 1A. And that's where the field currently stands. So here I will summarize this talk again, and now with more information that I have given to you. First, Hipparchus, it took you to 1 kiloparsec. Gaia took you to almost, improved it by a factor of 10, or maybe more depending on what stars. If there is a bright star further away, it will still get it, right? CFID variables, these are around 40,000 times brighter than sun. They are calibrated by Hipparchus. So parallax calibrates this measure of relative distance. It takes you to Virgo cluster, which is 20 megaparsec. Third, supernova 1A. This is billion times brighter than the sun. Again, this is calibrated by Virgo, by a CFID in the Virgo. Now you see a distance ladder has more than one step. One step was parallax, then CFID, then supernova. So this was actually calibrated by a CFID, but this can take you to a distance of more than a few thousand megaparsec. There are other relative distance calibrators, like there is something called Tully-Fisher relation for spiral galaxies. And as it turned out, the most interesting thing was this single cluster called Virgo cluster. There is a single cluster of galaxies called Virgo cluster, which is around 20 megaparsec, as I have told you many things. That allows you to do a relative calibration of at least 6 different measures. CFID, supernova 1A, Tully-Fisher relation, surface brightness and dimming, and various others. So that single cluster actually is very important for our building of the distance ladder, right? And this has been extensively studied, this cluster of galaxies, right? So this is where we stand with respect to extragalactic distances, but I have told you nothing about cosmology so far, right? And one fact about cosmology, which is very important, is, so before I come to it, I will just summarize this, is that in cosmology, the meaning of distance blurs. When you say in cosmology, if you ask the question how far that object is, that it doesn't have a well-defined meaning. So from luminosity, if you compute the distance, it's called luminosity distance. If you compute the using angular diameter relation, it's called angular diameter distance. They do not have the same meaning. So I will return to this point, but first I will ask the following question. If whatever I have told you is true, then one thing is true, one thing is clear to all of you. Distances are known to only a handful of objects, right? Very, very special objects in the universe, to them we can measure the distances. Otherwise, I can't measure distances. So how do I measure distances to a typical star, for instance? Typical star, mostly I can't. What is done is, like HR diagram I have shown you, typically the luminosity of a star correlates well with, the brighter the star, the higher its temperature is. Temperature can be measured from its spectrum. So I can say what its luminosity would be. So this is what is typically done. Measure the flux from a star, spectral type from spectrum, main sequence star. So it will give you some idea about the distance to it. What is important now is that some of these are being calibrated with Gaia. In the last 10 years or so, they have been calibrated with Gaia. So typically 90% of stars are on the main sequence. So I can measure distance to them. But what it also tells you, if I have a star which is not a main sequence star, and that might be nearby, I have no way of computing distance to it. How do I do that? Isolated star, right? How do I measure distance to it? I can't measure distance to an isolated star which is not on main sequence. So still majority of objects in our galaxy, we haven't been really able to measure any distances to them. Why? Because it's not possible. I have to apply one of the methods I have been talking about, and if that method is not applicable there, distance is not possible. So having said so much about galaxy, let me jump ahead. So this is the HR diagram, and of course, you have to be here, sun is here. So if you are on this sequence, 90% of objects are, I can measure the distance. There are many objects, many stars I can see with eyes, like they are giants. One of them is Betelgeuse, like, which you actually can see with bare eyes. It looks brighter than distance to it is not easy to measure. Why? I mean, to that we can actually, but otherwise it's not easy. So for instance, to white dwarfs, most of the white dwarfs, we have no idea what their distances are. Similarly, most of the supergiants, very difficult to measure distances to. So we are lucky if we are on this, 90% of stars we have a rough idea. But majority of other objects, we have no idea. If this is our galaxy, what about extragalactic? I have told you 1000 megaparsec already, right? But one fact I did not tell you about, and which I am going to in the remaining part of my talk, is the universe is expanding. Things are stretching in the universe. One galaxy is going away from the other. Where did I use that fact? I didn't use that fact, not yet. Because I kept saying distance to the supernova is 1000 megaparsec, right? But in fact, in an expanding universe, it is not possible to define a unique distance. This is true of general relativity. And it is too complicated, so I will not go into detail of that. Just make a note of that, you can read about it yourself. Distances to objects in general relativity are not unique. In this case, I have written here only one equation here, which is beyond the school level for sure. This is called a metric, which measures distance between two space-time points. So take 2 points, but they are space-time points. You define a time, you define a space, and you measure distance between them. And in the case of universe, the universe is homogeneous and isotropic. And that is one fact which we know about the universe. Homogeneity means if I move from one place to another, right, the universe still looks the same. Isotropy means if I stand here and look around me, everywhere the universe looks the same, right? So clearly you may ask, that is not true when I am on Earth, right? Like the here is not the same as there. So there is a question of scale here. If you stand at a galaxy and look at other galaxies, you actually do find a near homogeneous and isotropic distribution. And this was one of the biggest discoveries of Hubble, that the universe does seem to be homogeneous and isotropic. At present, we have verified this isotropy and homogeneity in many, many different ways. Isotropy of cosmic microwave background radiation, X-ray background, and many, many different ways. But the point being made here is that the universe is expanding, right? In an expanding universe, we have to redefine distances. And that's what I am actually going to try to do. So, the more important thing in an expanding universe is something called the Hubble's law. From the metric I had shown you, you can derive the following. The further the object, the faster it is moving with respect to us. They are all going away from us. Universe is expanding. The object is moving away from us. Nothing is coming towards us. But the further it is, the faster it is moving away from us. And that's called Hubble's law. And Hubble's law is a fundamental law of an isotropic and homogeneous universe. So you would say, okay, now what distance is that? That will depend on the setting. If it is luminosity distance, if it is the flux of an object, then it's luminosity distance, right? We have to measure the distance. So we have to measure the distance, we have to measure the speed, and then we have to do this correlation, right? Here again, I will be very, very brief with this, and I'm moving off to areas like which you'll be very uncomfortable with, but be with me for another 5-6 minutes. What we can actually see is that scale factor, the rate at which it stretches, we can solve for the scale factor using a cosmological model. And as it turns out, the universe could actually be accelerating. The universe is expanding, but it's not just expanding, it's accelerating. And that's a very important fact. It's an accelerated expansion. And that is something that we have verified, and that is what won the Nobel Prize in 2011. They verified that the universe is indeed accelerating. And that has to do with what the content of the universe is. We have matter in the universe, we have radiation in the universe, we have something called cosmological constant in the universe. And a combination of all of these three is such that the universe today is showing accelerated expansion around us. Most important point that I wanted to draw your attention to was this. I have explicitly defined luminosity distance. This is a distance which gives you the relation between the flux and the luminosity of the source. And this is defined in a complicated way. It's a pretty complicated relation for an expanding universe, and I have used it already, but defining it now. So you can actually measure A in a different way, Like you can look at the dynamical content of the universe, or you can do it in a kinematic way. You can take an object and expand the distance to it in terms of the derivatives. And the first derivative will give you Hubble's law, the second derivative will give you what's called the deceleration parameters. And so you can actually construct further and further off you can go. And this way you can actually find a relation between the distance to the object and its redshift. So this is Hubble's law written in a more complicated way. If I were to linearly expand it around a point, this is what it would look like. This is Hubble's law. Luminosity distance, h0 is a constant, and this is redshift. So linearly, if z is much smaller than unity, this term is precise, is unity, this is negligible. So this is the Hubble's law. Luminosity distance is proportional to redshift, which gives you the recessional velocity. So this is how Hubble's law is derived. So why am I saying all of this, right? I'm boring you a little with details that I gave you a lot of interesting geometry to start with. Now I'm taking you into general relativity and bit of that. The reason is I couldn't do without it. I could have made simpler models of it, but I wanted to give you a sense of what is involved here. Why is Hubble's law important? I will come to that. But first, look at what Hubble's law actually gives you. With supernova 1A, you can actually go to redshift of 1.4. This one redshift of 1.4, this data is around 500-600 supernova 1A. So CFIT will take you somewhere, CFIT will take you somewhere very close to 0. Right? That redshift would be close to 0.01. This takes you to redshift of 1.4. So this is the deepest look into the universe. It has made a jump from very local universe, 20 megaparsec, to a few thousand megaparsec, right? But keep in view that this distance, the way it is defined, is what's called the luminosity distance. And I will specify just now why I have actually spent so much of time on Hubble's law. So this is the deepest look that we have got into the universe, but yet again with a handful of objects. It's not that we have a lot of objects. So again, when you look at what I have said so far, you have handful of methods of measuring distances in the universe. Direct methods. Parallax, handful of other methods which takes you not beyond the local universe. Then you have some very special objects called CFIT variables, which allow you to go to 20 megaparsec when they are available. Then you have even rarer objects called supernova 1A, which allow you to take you to 1 megaparsec. Sorry, 1000 megaparsec. We have no unique method of measuring distance to a typical object. For stars, HR diagram gives us a sense, right? How about a galaxy? Suppose I want to measure the distance to a galaxy, right? We always say that galaxy is very far away. How do I know how far away it is? I need to have one of those distance measures to stick there before I can say how far it is. So what we do is the following. We calibrate using Hubble's law. What does Hubble's law say? The further the object is, this is Hubble's law. Right? Redshift can be measured from Doppler redshift. Right? We look at the spectra of the object and we see how much it shifts. Redshift can be measured very easily. Distance can't be measured easily. This H0 is measured quantity from local sources. Handful of local sources we have measured H0, right? So if I look at a galaxy and I have no idea what its distance is, we invoke Hubble's law. We say, okay, hang on, I can measure the redshift of that object, isn't it? He said, yeah, the redshift of that object is 0.1. I said, okay, if it is 0.1, then this is 0.1, this is known to me, I can measure the distance to that object using this relation. And most of the extragalactic distances that we actually measure or report measuring is just based on this technique, which is, by the way, not direct at all. The point I wanted to emphasize is a completely indirect way of looking at it. Direct measurement to galactic distance is almost impossible. But once I know its redshift, once I know how fast it's moving with respect to me, I say, okay, faster it is, the further off it is, and there is a relation, this very simple relation. I will use that simple relation and quote a distance to it. That's what we do all the time. So now I'll summarize my talk. First fact, distances to most objects in the universe cannot be determined directly. I mean, I think I've conveyed it to you, right? No, it's a very difficult thing to measure distance. You need to do a lot of work to measure distance to anything, at any distance practically. Second, distance ladder is built from the nearby universe, a point I have emphasized many times. Absolute distance using Gaia parallaxes, 100 kiloparsec you can go to. Calibrate standard candles, CFID and supernova 1A, which takes you to 1000 megaparsec. There are other standard techniques which I have not discussed and I do not have time to discuss. Standard rulers, Sunya's-Zeldovich effect, Baron acoustic oscillation, they also take you from a few megaparsec to a few hundred megaparsec. They are a parallel way of looking at things. And we are always trying to cross-calibrate these techniques whenever this is possible. It's not easy. Like, you see, you may wonder if you have a standard ruler and standard candle all in the same object, would that not be good? It's not easy. It's not easy. How do I know if I'm going to get that, right? I have to be lucky. You have to be lucky while observing something. There is only one standard siren. One. So what you really need to find distance to this object is what you also need a redshift to that object, right? So there is only one gravitational waves. Most of the gravitational waves that have been seen so far since 2017, they are black hole mergers, and we have never been able to find an optical counterpart to those terms. Because we do not have an optical counterpart, I can't measure the redshift to that object. One case it was possible, which is this, which was again in 2017, where they were actually able to find their optical counterpart, so they could measure the redshift. Once you have it, you can say something about, so this was the only measurement in Hubble diagram which comes from gravitational waves. Just one case. This is going to build as years go by. Gravitational waves, more and more such gravitational wave candidates would be seen. This was a neutron star merger. From at least that was the theory, right? This was one of those very rare cases. So this is the future for many things. It's going to be standard sirens. Again, distance to a typical galactic object, use HR diagram, main sequence stars, you can say something about. More recent Gaia data actually allows you to calibrate this measure. So you can be safe that if you have a bright object in our galaxy, a star, and it's on main sequence, we will have a rough idea of what its distance is. Faint objects, less so. How do I measure distance to an extragalactic object? I use Hubble's law. I have no independent way of doing this, right? I simply say there is a law that says distance and redshift are correlated. The proportionality constant has been determined using a handful of objects in the low redshift universe or all this building distance ladder that I told you, right? CFIDs, supernova 1A, all cross-calibrated with parallaxes. So that allows us to compute H0, Hubble's constant, and once I have it, I can confidently say what the distance to that object is. I have put distance here like this because the distance is not well defined when I go into the extragalactic universe. What does the future hold for us, right? I'm talking to school students, so the future is important. Some of the things which are being discussed now are absolutely crazy, I must tell you that. I mean, I think I find them absolutely crazy because I'm too old now, right? I believe that I will not see these things. So you see, for instance, universe is expanding, right? So I measure the redshift to that object, but that is expanding, that's a snapshot of what that object was. If I go and see that object few years later, can I see the change in that redshift? Can I? Possible? You agree with me it should be possible? Right? Well, not yet. And that would be another measure of distance actually, if that becomes possible ever. Right? This is something people are talking about it. People with my age group, they find it crazy. When you start reading it, maybe you'll find it exciting because this might happen in 3 decades, 2 to 3 decades. Right? So you people are still young enough to see this. Another thing that is being discussed, of course, is extragalactic parallaxes. Doing a parallax with Gaia was hard enough, but it is possible to do extragalactic parallaxes, especially with point objects. I mean, it is not easy, but it might be possible. So this is yet again some of those things you go into the field and you would explore, some of you, if you go into the field. And this is an interesting, peculiar velocity measurement might be possible, and this is something which people are already talking about. Point objects, peculiar motions, close to black holes. right? And this is becoming possible also because in millimeter waves now, we have interferometric measurement with very precise angular positioning. We are getting to angular positions far, far better than in micro arc second now, especially, for instance, with Event Horizon Telescope. So this might be possible too in the near future. And all of it will feed back into a more precise distance measure of even further off objects in the universe. So I think I'm done here and I'll stop. Thank you very much.
Get the mic. Hello.
Can I sit? I'll sit now. Sure, please.
The many scales that you have mentioned, right? And are they continuous or they are discontinuous?
They're discontinuous.
Of course, they are discontinuous.
Look, that depends on, you have to be lucky. CFIT is a lucky discovery. Supernova 1A is a lucky discovery. So if you're lucky, you get something and you jump from one scale to the other. You might find something else tomorrow, which might allow you to do intermediate region. Yeah, so it is discontinuous.
And also use different calibration for different scales.
Yes.
And they are not correlated maybe. The different scales are not correlated.
We believe that. If they are, we are in trouble. So actually, yes, I mean, we have no reason to believe why they should be correlated. Because they are completely independent objects, right? A supernova 1A and CFIT. But when you measure something, measuring techniques might bring in some correlation, which are not very easy to quantify. But yes, in principle, they are not correlated. They are completely uncorrelated. So we can use one to calibrate the other. Otherwise, we couldn't do that.
Sir, may I ask you, see, considering the fact that it is difficult to measure the parallax of stars which are a little bit far away, okay? But how do we measure the extra galactic parallaxes, in fact?
Yeah, so the whole point is...
That is the challenging thing, isn't it? What kind of technique has to be used for this kind of?
See, 10 megaparsec means I'm talking about a parallax of 1/10 of a micro arc second.
Yeah, yeah.
I'm talking about 10 power minus 7 arc seconds.
Yeah, yeah.
That is possible.
That's possible.
That is possible today.
Yeah.
But what is difficult is to find an object which is near point object.
Yeah, that's the
So our stars are near point objects for doing this work in our galaxy.
Yeah.
Extragalactic galaxy movement can't be seen. It's an extended object. But a maser like a water maser I talked about, that is a very near point object.
Yeah, yeah. But if we can measure through some technique extragalactic parallaxes and find out the distance to stars in other galaxies, then the same technique can be used much more easily for finding out the distance to stars in our galaxy also.
Sure.
Obviously.
Absolutely, absolutely.
That
Fainter
is,
ones.
Obviously.
Fainter ones, absolutely.
Thank you.
It will also help.
In addition to supernova, and CFIT variables, of course. Thank
See,
you.
like that NGC 4-5-8.
That kind
if those water measures, if somebody could measure parallaxes to those, that would be very helpful.
Good. Yeah, that's a new technique in
Absolutely,
fact, how we measure parallax.
People are
Fantastic.
discussed it,
Yeah, yeah.
not firm.
Yeah, it's so logical, really.
Yes,
thank you
yes.
very much.
Yep.
Excuse me, sir.
Yes, please go on.
Sir, what level of accuracy can we get? Because since it's always expanding, the universe, what level of accuracy can we get?
For doing what?
By seeing the distance between stars.
So, see, you are measuring the distance to the object when the light started from there. That is accurate.
But, okay. But if we check it after a few decades, then it will be different.
Yes, but you see, So I should tell you what the difference will be.
The
So
level of difference.
The level of difference.
Yeah.
So you see, the universe is expanding at a rate. The expansion rate is roughly 1 part in 10 to the power 17 seconds. 10 to the power 17. So the rate is 10 to the power minus 17 per second. Per year it's around 10 to the power minus 10. Right? That's very small. Universe expansion is not that large.
So we don't take it into consideration?
We do, but we can't do anything about it. That's what I said. The last point I made about z dot is that would you not, that's the question you really are asking in some way. What is the effect of the fact that the object has moved again? Right? So suppose I measure now, I measure after a few years, it has moved. Can I measure that?
Yeah, can you measure that?
Okay, so let's try to compute how would you do that. So let me give you a number. So that rate is 1 part in 10 to the power 17. Okay. The best spectral measures we can actually have, right, are roughly 1 in 10 to the power 10. Best. And you have to be lucky for that. So we are 7 orders of magnitude off from there. Right? So we are very far away from it. Yet we can reach there because if I look at a million objects, all million objects are behaving the same way. Right? If I wait 10 years, I can improve it further.
Can we?
We can try. See, this moving cluster method has been done for 60 years. See, many of these things I'm talking about have been done over a period of 4 to 5 decades actually. So astronomy's lifetime is large. So you might do a PhD, you will start a movement, but like the point is your grad students might actually figure it out. Yeah, that's the way it works. In fact, there is a tradition of that in Hubble's sequence. I mean, the people who started it in 1930s, it is their great-grand students who actually figured it out, long after those people are actually dead. So yes, absolutely, it will be done. So people will try it. Okay, so far it is not possible, but it's going to be difficult, but let's see.
Thank you, sir.
Sir, what is the purpose of finding the distances of all the stars?
How do you know how further? I mean, the point is like you want to understand the expanse of our galaxy or the expanse of our universe. How will you do it? How else will you do it? Suppose I told you, right, all that you see on the sky is just outside the solar system. Would that be exciting? You see my point? All these galaxies, everything is just outside the solar system, right? No, much less exciting, right? So we want to understand the expanse of our galaxy, expanse of the universe. It's a normal human quest in some way, right? So that's the exciting part of it. But what I was trying to convey to you is that whether it is just outside our solar system is not an easy question, right? There are objects which could well be outside of our solar system because we have never measured distances to them. Or they could be like 100 megaparsec. True.
So if some star or any object is nearing us, we can find out, and if any measures can be taken.
See, that's what I'm trying to say. I have given you a list of techniques that we use to find distances to those objects. There are a handful of other techniques and that's it. So not really true. If a star is coming close to us, I don't know what the distance to it is. How will I know the distance to it? I can find spectrum, I can find that it's coming towards me, that I can find, right? But I don't know what the distance to it is. That was the whole point of my talk. There is something called fast radio burst, which was discovered only in 2005. This discussion rages on about them even today. There was something called gamma ray bursts, which were discovered in 1980s and 90s. The same debate raged on about them for a while. So this is not a debate that goes anywhere. This goes on and on. On the one side sits a person who says, they are very far away. On the other side sits a person who says, no, quite close actually. Unless we have an indirect way of measuring distance to them, we can never really settle this question, can we? So this question is again and again asked about near and near objects. That's the point I'm trying to make. Like fast radio bursts, this question is being debated right now. It's an ongoing area of research, by the way. Very active area of research currently. And gamma burst only question was only settled in 1990. So yeah, it's an ongoing quest.
Thank you, sir.
So you talked about standard sirens, and you said we can find the distance using the waveform of the gravitational wave. Can you elaborate on that a little bit?
See, the waveform of a gravitational wave is what's called chirp. Gravitational waves, like waveform is like a chirp. Chirp is what birds do actually. So what happens is, when you hear a bird, right, the frequency of increases and so does the amplitude. Hear a bird carefully. That's what a bird does. It starts like this. The amplitude is small, frequency is small, but frequency increases and so does the amplitude. That's called a chirp, right? So gravitational waves are also, the waveform is like a chirp waveform. But in that waveform of chirp, we have information actually about what the parameters of the gravitational binary, of the binary were. The parameters like mass, what was the distance between the two binaries when the gravitational wave was emitted, and such like orientation on the sky. All of these parameters can be extracted from that measure, which means I know its luminosity. Once I know the luminosity, once I have all these parameters, I can compute how much energy was released at the point where it's coming from. And I know how much I've detected. So yes, I can say something about distance to that object, except to be able to put it in a Hubble diagram, I need to get its redshift also, which has just been possible in one case. So yeah, I can say from the chirp waveform, and reconstruct it.
But if it's only just one candidate, how can you call it standard? You need
No, the standard part is actually in the modeling of the chirp waveform. See, when I model a chirp waveform, right, a chirp has information about all the parameters of the gravitational wave binary. Theoretically. Theoretically, I can construct it. I can test it once in a while. Only one case it has been tested. Roughly. It gave an H naught of 70. It roughly matched. Roughly. That was not a great match. The error was much larger than the usual cases. But it roughly matched. It seemed to suggest we are on the right track.
If there are no further questions, can we conclude the session by thanking Professor Seth again for giving this wonderful talk. Thank you very much, sir. Yeah, I request all of you to have a high tea that is served outside. Please have the high tea before you go. Thank you very much.